Alright class, so we've been talking about redox reaction and balancing redox reaction. We're going to continue to that and get a little bit fancier now. So here is an example of a redox reaction. Now, one thing we've done, and you know how to figure out what's been oxidized, what's been reduced, what's oxidizing agent, what's reducing agent. You know how to do that. We've been going over it. Now, here's one piece of information we haven't talked about. So here is the redox reaction I've given you. Would this redox reaction happen spontaneously? What do you think? Before, if I gave you a double replacement reaction, you would look at the solubility rules and then figure out what happens if there is no reaction or if a precipitate would form. Now, how about for redox reaction? Just because I give you a redox reaction doesn't mean this reaction is going to happen spontaneously. How would you know if this reaction will happen or if the reaction will be a no-go? Now, for that, what you would look at, you would have to look at SRP table to see if this reaction will happen or if this reaction would not happen. What is that? So here is an SRP table, standard reduction potential. Standard reduction potential. Okay, now I want you to look at this SRP for me. If you look at the SRP for me, what you would notice is that all of these are half reaction, right? They're all half reaction, and for each half reaction, a cell potential is given. Okay, so these are all half reaction, and a cell potential is given, and all of these cell potential are measured against the standard. What is our standard? Right here. Okay, we basically said here is 2H plus going to H2. Okay, now we're gonna set this to be 0. That's going to be a standard. So we measure everything against H2. So we measure everything against H2, and then we come up with this cell potential. So one more time, again, these are all half reaction. All these half reaction have a cell potential and is measured against the standard, which is right here. This is our standard, H plus going to H2. We set this one to be 0, so we measure everything against this. Now it's usually measured at a standard condition, standard reduction potential, or a standard condition. What is a standard condition again? So remember, standard condition are 1 atm, 25 degrees Celsius, which would be 298 Kelvin, and also standard reduction potential, standard condition is 1.0 molar. This is really key. Before, we didn't have this for gases and when we did thermodynamic. So 1 molar solution. That's what it means, standard reduction potential. We measure by the standard, which is 1 atm, 25 degrees, and 1 molar solution. Okay. Now, the other thing, when you look at this table, that is going to stand out to you is that all the potentials are reduction half reaction. All of these are reduction. We gain electron, we gain electron, we gain electron, and get reduced. So all of these are reduction half reaction. Because remember, we had oxidation half reaction, reduction half reaction. Well, when you look at all this, if you look at all of these are gaining electron, aren't they? So these are all reduction. These are all reduction half reaction. Okay? So that's why I'm going to write down E of reduction. So these are all reduction half reaction. So the table only has reduction. Now, what if you want oxidation? Then what do? What do you think? If you want oxidation, what do you think you have to do? Yeah, you would have to reverse the sign of the reduction. Okay, so let's go over this again. So if you look at this table, all of these are reduction. Okay, all of these are reduction. So there are reduction potential. RED means reduction. This is my cell potential, and the not means standard. Okay, so all of these are reduction. Now what happens if I want oxidation? Remember, if all of these are reduction, if I flip it, then there would be oxidation, right? Look over here, for example. Let's do an easy one. Easy one would be like here. Zinc becomes +2 to 0, so zinc has become reduced. If I flip it, then zinc 0 would go to zinc +2, and that would be oxidation. So to get oxidation, you would just flip all these equation. If you flip the equation, what do you have to do to the sign? You have to flip the sign. You have to reverse the sign for the reduction to get oxidation. Okay, so hopefully you're following that so far. All right, now to know if a reaction is going to happen or not happen, to see if the reaction is going to happen spontaneously at a standard condition, what you would have to do, you would have to add up the reduction cell potential and plus the oxidation cell potential, okay? And if this number ends up being positive, what that means is you are going to have a spontaneous reaction. And if this number ends up being negative, what that means is you have a non-spontaneous redox reaction. So we need to do more work for this reaction to happen. Okay. So now that you know the basic, before we get more into this, get a little fancier with the table, let's go back and look at this reaction. So this was my redox reaction, and my question was, would this reaction happen or would this reaction not happen? Would it happen or not happen? Okay, well, let's figure out if that reaction would happen or that reaction would not happen. How do I figure it out? First of all, you need to figure out what's been oxidized and what's been reduced. What do you think? This one is easy. I'm sure you got this down. So copper is going from copper +2 to copper 0, right? Because here copper by itself has no charge, it's neutral. So if I go from +2 to 0, I got more negative. That would be my reduction. Okay. Now what happened to the zinc? Zinc over here is +2. Zinc over here is zinc solid. Anything in elemental form has a charge of oxidation number of 0. So I went from 0 to plus. I got more positive. What is that? That is my oxidation. Okay, you following me so far? Beautiful. So let's figure out what is the cell potential for this reaction. So what's going on? My reduction is what? My reduction is copper. Do you guys agree? My reduction is copper. So what I want you to do, I want you to look at the equation. I want you to look at the equation and see what is the cell potential for copper. So here or here, you guys see that? Copper +2 going to copper 0. Okay, +2 to 0. That's exactly what we have. +3 plus 0.34. You guys follow that? Okay, because that is my reduction. Now, what is my oxidation? My oxidation is zinc going from 0 to +2. Where is zinc? I have zinc here, but remember, this is reduction. What I want is oxidation. So I would have to flip this because this one is zinc +2 going to zinc 0 is reduction. But what I have oxidation. So all I have to do is flip this, because if I flip this, then I would have zinc +2 going to zinc 0. So because I flipped the equation, I have to flip the sign. So for oxidation, what you have to do, you have to flip the sign. So what it would be plus 0.76. If I add up all this together, I get 1.10 volt. That's the unit. Okay. Is the reaction will go? Yeah. This is a spontaneous reaction. This reaction will go. This reaction will happen. So far, so good? Okay. So here's how you would know if a redox will happen or redox will not happen. Now, before we go, just to do some practice problem, if you remember, what is my oxidizing agent? What's my reducing agent? This one gets oxidized, so this has to be my reducing agent. This one gets reduced, so this has to be my oxidizing agent. All right, beautiful. Okay. Now let's go back to this table. I just want to make sure you really understand this table. So if you look at this table, a few things to kind of look for. Now, since this is a reduction table, the more positive these are, that means these are really, really good at reducing. They want to be reduced. Now, if you're good at reducing, that means you are a good oxidizing agent. Because remember, they're the opposite, right? If this one got reduced, you're an oxidizing agent. If this one got oxidized, you're a reducing agent. Don't forget they're the opposite. So when I have up here, when I have a large positive potential value on an SRP, that means these guys, they really, really want to be reduced. Reduction is favorable. If reduction is favorable, what are you? That means you are a good oxidizing agent. That's why it says very good oxidizing agent, because if you like to get reduced, if you're favorable reduction, that means you're a good oxidizing agent. Now, as we come down here, okay, so these guys don't want to get reduced, right? That's why they have a negative values. They don't want to get reduced. Okay, what they want down here, they probably want to be oxidized, right? Because if you flip these signs, then this would be plus 3.05 for oxidation. So these guys want to be oxidized. So I want to put over here. So these guys basically, they want to be reduced. Okay, these guys on top, they want to be reduced. They like to be reduced, okay? Now, how about the guys over here? The guys over here, they want to be oxidized. And you can kind of see it because over here, we would have to flip the sign. If you flip the sign, these are all negative, these are all positive, okay? Now, this is really cool. And usually engineers complain about taking Gen Chem. Here's why you're taking this Gen Chem. Batteries. If you're an engineer, batteries are your best friend, right? Batteries have all these redox reactions going on. Your phone right now, you probably have your phone right next to you in your hands. What type of battery does your iPhone have? Lithium battery, right? Now, why did they come up with these batteries? Back in the days, cell phones, the battery was large, the battery was heavy, the battery would not last long. Now we have these amazing batteries in our iPhone. Because then they realize, hold on a second, look at this lithium. This lithium really, really want to be oxidized. So that's probably a good idea to put something that really, really want to be oxidized in those batteries. It's kind of cool idea, right? All right. So think about this. Your batteries are lithium and it has the oxidation reaction going on. Now, what I want you to do, I really want you to be familiar with this SRP table, okay? Now, to do that, let's do a couple practice problems to make sure you are really, really understanding how to use, okay, let me rewrite this, how to use this SRP table. So I'm going to write down this reaction, and what I'm going to ask you to do, I want to ask you to figure out, will these reaction happen or will this reaction not happen? If I add these two together, will they oxidize each other and reduce each other, or will they not? Will the reaction happen or not happen? So basically, will this happen? If I add copper metal and iron plus 3, if I add nickel plus 2 and silver metal, would that happen? If I add aluminum metal and zinc solid, will that happen? Okay. Now, you can do the math and figure it out, right? So basically figure out what's been oxidized, what's been reduced, and then add up the oxidation and the reduction, and then see if you get a positive number or a negative number. Or you can figure out based on the position on the SRP. Because remember what we said, the guys on top, they really want to be reduced. The guys on the bottom, they really want to be oxidized. So also you can look at the position on the SRP table to figure it out, or you can just do the math also. So let's do one together. So copper 0 plus Fe plus 2. First of all, if I add these two together, the first thing you need to figure out what will be oxidized and what will be reduced. Okay, what do you think? Now, here you know that the copper is 0, right? Copper solid by itself is 0. And remember, if copper is 0, if I have a copper metal, metals want to be oxidized. They want to become positive, right? Metals only lose electron. So if I have a metal that has a 0 charge, the only option it has is become more positive, because metals, they love to lose electron. They're going to become positive, right? So this is going to be my oxidation. And Fe plus 3 is going to be my reduction, because I can reduce it. Okay, so copper is my oxidation and Fe is my reduction. I'm going to put up the chart one more time. Now let's find copper over here. Where is copper? You guys find copper? Okay, so copper is over here, and then I have Fe plus 3 going to Fe. Okay, I have this one over here. So if you remember, we said that my copper is going to be my oxidation, and then Fe wants to be reduction. Do you think this is going to happen? You can add up the numbers, but you don't even need to add up the numbers, because what wants to be oxidized has to be lower than what wants to be reduced. Because everything on top really wants to be reduced, everything on bottom wants to be oxidized. So the one that gets reduced has to be higher on this table than the one that gets oxidized. That's one way to look at it. So will this reaction go? This reaction will go. Or the other one to look at it, there's another way we can do this. We can say, okay, this is reduction, 0.77, okay? This is oxidation, I have to flip it, okay? So we go 0.77, I have to flip it, so plus negative 0.34. Now, if I add up these two numbers, what do I get? 0.77 minus 0.34. I get 0.43 is a positive number. Yes, this reaction will happen. Okay, you can also look at the position. That also helps. All right, the next two. Do it, pause me, do it, and then check it with me. Now, this one, which one is going to get oxidized, which one is going to get reduced? That's the first thing to figure out. Well, here, silver has a charge of 0. If you have a metal and you have a charge of 0, the only option you have is really oxidation, because metals only have positive oxidation number, right? So this is going to be my oxidation, which means this is going to be my reduction. So I have nickel and silver, okay? So let's come over here. Find the silver and find the nickel. Hopefully they have it on here. This is my nickel, and then you guys see silver here. The silver exists on here. Yes, it does. Perfect. Okay. And we said silver is my oxidation and nickel is my reduction. Is this going to happen? This is not going to happen, because remember, the ones on top are the ones that really want to be reduced. My oxidation is on top. The other way to do this is just to add up the number. So here's my reduction, negative 0.28. Okay, so I'm going to write that down. So negative 0.28 plus, okay. Now I'm going to come over here. Now, this is my oxidation. What does that mean? That means I have to flip the sign. The plus becomes negative, right? So then plus negative 0.80. Okay, so you can already see that where I'm going with this, because both numbers are negative. This is going to be negative 1.0. Nope, this reaction is not going to happen. Okay, ready to do the last one? Let's do the last one. So here, which one is oxidation, which one is reduction? Hopefully you're yelling, duh. This one, zinc has a charge of 0. When metal has a charge of 0, it's going to be oxidation, because metal have only positive oxidation number. They have no choice but to go from 0 to positive, which means this one, it has plus, it could get reduction. Because remember, oxidation is you become more negative. If this one is 0, and oxidation is when you become more positive, reduction you become more negative. If the zinc has a charge of 0, so the only chance it really has for a metal is to go to more positive. Okay, so aluminum and zinc. Let's come over here. You ready? Aluminum and zinc. And sometimes, okay, aluminum is right here, and zinc is over here. And we said that zinc was my oxidation, aluminum is my reduction. Is this going to happen? No. Because on this table, the reduction has to be higher up. Or you can actually do the calculation and you're going to see, nope, this reaction is not going to happen. All right, so hopefully you got this down. Hopefully you understand this. So get familiar with this table. We'll give it to you on the exam. Just remember, the one on top, they really want to be reduced. The one on the bottom, they really want to be oxidized. Okay? And not every two combination is going to happen. Not because I give you a redox reaction doesn't mean it's going to happen, but you can figure out if it's going to happen or not going to happen based on the table. Okay, nice job, really nice job. Now here's the next thing. So I showed you all those fancy cell potential. Now how did they do that? How do we measure a cell potential? How did they actually measure all these things? Right? How do we measure E cell potential? Now, the way to do that, we use voltaic cell to measure. We use voltaic cell to measure EMF between two half reaction. So, basically what I want you to take out of this is that, remember, redox is a transfer of electron, right? And transfer electrons, basically that's electricity. What is electricity? Electricity is nothing but electrons. So redox is a transfer of electrons, right? I want you to remember that. I want to write it down because that's really key. That what redox is when you transfer electrons, okay? And electrons is what? That's electricity. Okay, so what we do, we can use a voltaic cell to measure the E potential. We can measure the electricity. We can measure how the electrons are transferred. And the other thing I want you to remember is that all batteries contain a voltaic cell. Now, next time what we're going to go over, we are going to go over the voltaic cell. All right, nice job. I will see you guys at next video.